Okay, well, I thought there was another page to this, so I quit here. But actually, we should have just been able to finish this. Alrighty. Let's see. Notice in number 4 and 5, the whole in the percent problem follows the word of. Remember, it is percent of whole equals part. So just identifying what the whole is, we should be able to do this. Okay, so show your work and answer in a complete sentence. All right. So we need to know what percent of pregnant women tested positive for pregnancy. So we're going to have percent of pregnant is positive. I like to take a sentence and kind of turn it into this half equation, half English, and then go straight for there. Okay, so the total pregnant. The total pregnant is 50, and tested positive is 45. Okay, so I know that X percent times the number pregnant is 45. I didn't choose my colors very well. These are two different colors of green. Okay, so following my equation now, if I divide both sides by 50, I get that X is 45 divided by 50, which is 0.9, or 90%. So if I want to write this as a sentence, I can write it as 90% of pregnant women tested positive. That's what they wanted to know, so I just went back to my original sentence here. Okay, what percent of women were pregnant? All right, so we need to go to, once again, our pregnant, and we also have to go to our total. So we want percent of total is pregnant. So I have X times 50, 500, excuse me, 500 equals 50. Percent of total is pregnant. So once again, I divide by 500, and I get X is 50 divided by 500, which is 0.10, or 10%. And once again, I go back to my original sentence and answer it. 10% of the women were pregnant. This is women. So 50% of the women were pregnant. Okay, what is the chance? So that's asking for a percent. What percent is that she is pregnant given a positive test? Okay, so since the woman has the positive test, that is going to be the whole. This one is worded very oddly. So positive test. So we want to know percent of positive is pregnant. Okay, well, our positive is 90, so X times 90, and so our total tested positive is 45 of those, 90 of those 45 are pregnant, so that equals 45. When I divide both sides by 90, I get X is 45 divided by 90, which is 0.5, which is 50%. Now, following along the same lines, there are a lot of ways you can write this. I'm going to make it sense. So there is a 50% chance that a woman is pregnant given that she tests positive. So, a positive pregnancy test means the chance of being pregnant is 50%. Compared to an overall incident test of 10%, which we found on the front. Okay. Well, since we have a little bit of extra time, I'm going to go ahead and talk just for a minute about Simpson's paradox. This is not something you're going to be tested on, but I did want to show it to you because it is just a way of looking at, and I'm going to go through this very, very quickly. This is just a way of looking at averaging averages. Okay. All right. So we talked about this when we were doing baseball, when we were looking at that fallacy, and Simpson's paradox is the result of that. Okay. So we know, just like at-bats, it's the number of hits versus divided by the number of at-bats. Your shooting averages is the number of shots made divided by the shots attempted. So let's look at Tony Parker and LeBron James. LeBron is 4 for 10, 40%. Tony is 1 for 4, which is 25%. So this is for the first half of the game. So LeBron won. He had the highest average. In the second half of the game, LeBron got 3 out of 4, which is 75%, and Tony got 7 out of 10, which is 70%. So the better record was LeBron. Okay, well, based on this, he had the highest percentage in the first half. He had the highest percentage in the second half, so one would think that it was a better shooting average for the game. But here's the deal. This is where the averaging averages. We have to look at the total number of shots. Okay, so if you look at the total number of shots for LeBron that he made, he got 4 plus 3, which is 7. And he attempted 10 plus 4, which is 14. Tony made 1 plus 7, which is 8 out of 14. And if you do those averages on the whole thing, then LeBron's average is 50 and Tony's is 57. So Tony had the best overall average, and it really was not like the prediction. Okay, so it's counterintuitive, and we talked about this when we did averages of averages. So that is what Simpson's paradox talks about. And again, I just wanted to show you what it was really like. So we're going to do this example, and I think we'll just finish up with the definition of it. Okay. Let's see how we can figure out how this happened. LeBron was better in each half, and Tony is better overall. Okay. But it is, again, because of the difference in the total number of shots and the total number of I'm sorry, the total number of attempts and how many baskets they made. That is what Simpson's paradox is. A set of data may give different results for each of several group comparisons than it does when the groups are taken together. All right. So this next one just gives you an example about drug trials and about deaths from TB. We have enough death and destruction going on right now. I really don't want to do another example about deaths. But if you'll notice, here, if we look at white versus non-white, the populations are so different that the percentages can be deceiving, and you need to look at the overall rates. Where here in Richmond, the white versus non-white, there is not as much disparity, so the percentages may not have the same meaning. Okay, so I've gone on enough about this. This is the last information that will be tested on the Unit 2 test, and it won't happen today, but it will soon, that I will get the summary and video on there. Okay, thanks.